The second video looks at the main components of predictive control. So we've established in the first video that using prediction, or anticipation if you prefer, within control design is logical and something that humans do naturally. And therefore it makes good sense to consider how we can take this concept and embed it into an automated control strategy. So this video is going to look at the core concepts which underpin the use of prediction in control design, and later videos will gradually consider each of these concepts in more detail. So what are the main components of a predictive control law? I'm just going to list them for now. You've got prediction, this concept of a receding horizon, modelling, a performance index, degrees of freedom, constraint handling, multivariable, and in fact you could list more, but these are the main ones. So here's the key point. The key to effective implementation of a predictive control law is a clear understanding of how MPC works, and that means a clear understanding of all of these components and how you should approach them. And what I would say is readers should not attempt a predictive control algorithm design or tuning before they properly understand all these components and how they're working, because otherwise they will make silly mistakes, and the literature is full of silly mistakes, or they could end up with a rather poor implementation. Let's do each component in turn then, and we'll start with prediction. Some of the questions you might like to ask are listed next. Why is prediction important? And we've sort of done that in the first video. How far should we predict? What are the consequences of not predicting? How do we actually go about prediction? How accurate do predictions need to be? So you'll notice we've given a number of key questions there. And what we're going to do is we're going to use some simple analogies which will help the viewers explore these and give you an understanding of what might be good or appropriate answers. And again, we reiterate that you shouldn't attempt a predictive control design until you properly understand answers to questions like these, because if you don't understand the questions and the answers, you won't understand the predictive control law that you've just implemented. So why is prediction important? Now, anyone who's a parent or a teacher or something like that will no doubt be totally fed up with telling their children to think of consequences before they act. It's something that children are particularly bad at, thinking through consequences. Some examples. They just jumped off a shed roof and they ended up with a broken ankle, which probably could have been anticipated as a high risk. They used a knife incorrectly or carelessly and they ended up with a badly cut finger. Hopefully they didn't cut their finger off, but it could be done. They spoke back at a teacher because they were a bit irritated or whatever, but what happens is they end up with lots of detentions and should have just kept their mouths shut. They didn't consult a bus timetable before they went out and just turned up at the bus stop, hopefully, and then had a very long wait at 11 o'clock at night. Now, you will be able to come up with lots of your own examples, and the key thing here is before you plan an activity, what do? You think through all, and that's a key word, all the likely consequences and possibilities, because if you haven't, the outcome may be far from desirable, because the outcome might be something that you hadn't really thought about. Now here's the next question. How far ahead should you predict then? Well, the prediction horizon is often misunderstood concept in the literature and in predictive control, and by many people it's treated as a tuning parameter, and it's not actually a tuning parameter. If you think it is, then you're generally misguided. In terms of normal human behavior, we all know how far ahead we should predict and the consequences of getting this wrong. So that's all you need to do, is reflect on what humans do, and then you will get the prediction horizon correct. So we have some examples here. When you're driving, what prediction horizon do you use? So how far ahead do you predict the behavior of the car? And what happens when it's foggy? How does this change? Well, here's an example. You always predict beyond the safe braking distance, or well beyond the safe braking distance in general, because otherwise you cannot give a reasonable guarantee of avoiding a crash. So I've summarised that as your prediction horizon is always greater than your settling time, and your settling time is clearly linked to the braking distance. If you want to heat a house, what prediction horizon are you going to use and why? Well, again, this should be fairly obvious. You'll consider the time at which the house needs to be warm enough, and then we turn the heating on sufficiently far in advance so the house is warm enough, and that is beyond the settling time. So again, you'll see the prediction horizon has to be greater than the settling time of the system, because otherwise you can't get the outcome that you want. If you're moving a very heavy item around the house or the garden or something like that, what prediction horizon are you going to use? Well, again, what you do is you consider the whole trajectory. The lifting, the carrying, the putting down again, because if you don't, you might drop the item at a place which causes serious damage to you or something else. And again, you see the prediction horizon has to be greater than the settling time. So a summary: common sense analysis of everyday scenarios tells us we must always predict beyond, and that's a key word, beyond the key dynamics of a process. Because if we don't, the dynamics that we have not observed, that's the key word, not observed, and thus excluded in our decision process, those are the very dynamics which could come back and bite us and give us an outcome we didn't want. So, for example, if you only predicted 20 meters ahead while driving at 70 miles an hour, and then there was a sharp corner 20 meters ahead, what's going to happen? Of course, you're going to crash. You've not predicted far enough ahead. If you only predict 20 minutes ahead when you're trying to heat the house, then clearly the house will not be warm enough in time, because typically houses take, 1.5 to maybe 3 hours to warm up. If we only plan 3 meters ahead while carrying a heavy object, we may not allow for a critical obstacle en route, and that could cause us a few problems. Right, next concept then, receding horizon. Now again, this is a concept that is often overcomplicated in the literature. In fact, it's very simple indeed. All it means is that we continually update our predictions and decision making to take account of the most recent target and measurement data. You might say, well, that's pretty obvious. You continually update your decisions. Of course you do. Well, that's all that the receding horizon actually means. Now, the effect of this is that the prediction horizon is always relative to the current position, and thus the far end of the horizon recedes away from the viewer as the viewer moves forward. So we've got a few diagrams here to show you what we mean. Imagine that you've got a current position marked by this box, and you're predicting to a position some far in the future. So that's the second box. So here we go. Time t equals 0, there's your prediction. So you predict from a start point, you see I've marked there, to an end point, which I've marked there. Now, if you go forward in time, you will have moved forward. And so your start point has now moved to here. If you have the same prediction horizon, you're now predicting to a point which is further. Okay? And similarly, when you get to time t equals 2, you'll see again your start point has moved, and therefore your end point has moved. And that's all that receding horizon means. It means that your end point moves away as your start point moves forward. And hopefully you say, well, that's rather obvious, and you'll see that the horizon always stays the same. The actual distance that you're predicting is staying the same. It's just that the end point is moving. What about feedback? How do you get feedback from predictive control? And many viewers will hear the argument that it's the receding horizon that introduces the feedback, and actually that's a bit of a confused statement, and I would put it rather differently. I would say that what gives you feedback is the continual update of the predictions and the associated decision making to take account of the most recent target and measurement data. And anyone who understands feedback will see that it's in fact this statement which gives you feedback. So measurement is a core part of a feedback loop, And so it's the update of the predictions using the most recent measurement data is required in order to give you a feedback loop. The other thing is the decisions on what am I going to do with the control have to be based upon the most recent measurement data. And so what did you see here is the update of the decision making, which actually closes the loop. So you have measurement and decision, and it's these two together which actually give you feedback. And you'll notice, of course, predictive control incorporates both, and therefore you have feedback. What about modelling with predictive control? Well, modelling is a core part of predictive control because you need predictions. Now, humans are very good at predicting outcomes, but if I asked you to say where do these predictions come from, you're probably going to struggle. And you say, well, you know, it's based on experience, I've seen it before lots and lots of times, but you'd find it quite difficult to untangle and automate what's going on in your head. You just know that you can do it. In order to automate predictions, to get the computer to do this for us, we need to be able to model system behavior in a bit more of a mathematical manner, and therefore we need a mathematical model on which to form our predictions. Now the next question is, alright, but how do we go about deciding or determining what is an appropriate prediction model? Well, there's a few questions that you might want to ask. First of all, we'd like the predictions to be easy to form. I know we're going to use mathematics, and some people say that's complicated already, but we don't want the forming of the predictions to be any more complicated than necessary. So ideally, we want a linear model if we can get away with it. We want the model parameters to be easy to identify. There's no point saying, oh, I've got this easy model form, but it's really, really complicated to identify the parameters, because then the model's not much use to me. And we also want the model to give us accurate predictions. But you'll notice these three statements are still somewhat vague. So can I be a bit more precise? What do we mean by accurate? Do we mean it gives good steady state predictions, or good transient predictions, or good mid-response predictions? What exactly do I mean? And when I have parameter identification to get my model parameters, what do I mean by I've got a good identification? Because if you look at most simple black box methods, you'll notice they're based upon one step ahead prediction errors, whereas in fact predictive control, you're more likely to be interested in steady state and mid-response, and the fast transients might be slightly less critical. So, modelling summary. We want the simplest model that gives accurate enough predictions. That's what we actually want. Okay, but accurate enough is ill-defined. Now in practice you'll find that often if the predictions are accurate to within 10 to 20%, certainly in the steady state, then that prediction model will probably be effective enough as long as it captures the key dynamic changes during transients. Now why is this? I've got down at the bottom. Basically the reason is that the continual feedback will correct for small modelling errors. So the fact that we might be out by 10 to 20% isn't critical, and you'll know that yourself from the things you do like driving. Your predictions are very vague, but you'll continually update them, and therefore you correct for any small errors. And why is that important? Because it says it's rarely beneficial to spend excessive effort improving the accuracy of your models if this is unduly expensive or time consuming, because often the increase in the improvement in the accuracy of your predictions may have very little impact on the closed loop behavior. Now, key thing at the bottom, your model has to give you good long range prediction, because that's one of the key components of predictive control. If the long range prediction is totally out, then using this model will not be very wise. So at this point, because this video is long enough, we're going to suggest you move to video 3.